Welcome to today's video, where we'll be diving deep into the fascinating world of operational amplifiers and exploring the concept of using an op-amp as a differentiator. Specifically, we'll be focusing on the inverting differentiator configuration and examining its behavior using a simulator. Before we delve into the circuit details, let's take a moment to understand what a differentiator does. In the realm of signal processing, differentiation refers to the amplification of the rate of change of a signal. It essentially highlights the high-frequency components of an input waveform, providing us with valuable insights into the dynamic behavior of signals. Now, let's turn our attention to the circuit setup in our simulator. We have a 5-volt, 60 Hz triangular wave serving as our input signal. This signal is connected in series with a 2 microfarads capacitor, which is then connected to the inverting terminal of the op-amp. Additionally, we have a 5 kilo-ohm resistor connected as a feedback resistor. The purpose of the capacitor in this configuration is to introduce a time-varying element into the circuit. As the input signal changes, it causes a current to flow through the capacitor and the feedback resistor. This current, in turn, is amplified by the op-amp to produce an output voltage. Now, you might be wondering how this process results in a differentiator effect. When we observe the output waveform on the oscilloscope, we can see that despite the input being a triangular wave, the output appears as a square wave. This square wave output is a clear manifestation of the differentiation process. To better comprehend this phenomenon, let's delve into the inner workings of the circuit. When the input signal experiences a change, it induces a current to flow through the capacitor and the feedback resistor. This current acts as a differentiator, emphasizing the high-frequency components of the input waveform. In our circuit, the feedback resistor, in conjunction with the capacitor, creates a time constant that governs the charging and discharging rates of the capacitor. The time constant, denoted by the product of the resistor and the capacitor values, effectively determines the frequency response of our differentiator circuit. By adjusting the values of the resistor and capacitor, we can manipulate the time constant and consequently control the cutoff frequency of our differentiator circuit. This flexibility allows us to tailor the circuit's response to our specific needs, accommodating various input signals and frequency ranges. However, it's important to note that while the concept of an op-amp differentiator seems straightforward, practical implementations come with their own set of challenges and limitations. Op-amps possess characteristics such as slew rate and input bias current, which can impact the performance of the differentiator circuit. The slew rate refers to the maximum rate of change an op-amp can handle, and exceeding this limit can lead to distortion in the output waveform. The input bias current, on the other hand, introduces an additional current flow into the circuit, which can affect the accuracy and linearity of the differentiator. Therefore, when designing practical circuits utilizing op-amp differentiators, it is crucial to carefully consider these factors and select op-amps that meet the required specifications. In conclusion, we have explored the op-amp as an inverting differentiator configuration in this video. By utilizing a simulator, we observed how a 5-volt, 60 Hz triangular wave input, combined with a capacitor and a feedback resistor, resulted in a square wave output on the oscilloscope. Understanding the behavior of differentiator circuits can be invaluable in various applications, such as signal processing, frequency analysis, and waveform shaping. It provides us with a powerful tool to accentuate specific frequency components and extract information from complex input signals. I hope you found this video insightful and informative, expanding your understanding of op-amp differentiators. Remember that experimentation and exploration are key to mastering this concept. By adjusting the values of the components and exploring different input signals, you can further explore the capabilities and limitations of the op-amp differentiator. As you delve deeper into this topic, you might also encounter additional variations of the differentiator circuit, such as the non-inverting differentiator configuration or the use of multiple stages for enhanced performance. Furthermore, it's worth noting that the op-amp differentiator is just one piece of the puzzle in signal processing. It can be combined with other circuits, such as amplifiers, filters, or integrators, to create more complex systems tailored to specific application requirements. Understanding the theory behind the op-amp differentiator and its practical implementation will open up a world of possibilities for you in the field of electronics and signal processing. You can apply this knowledge to a wide range of disciplines, including audio processing, telecommunications, control systems, and many more. Remember, practice makes perfect. I encourage you to experiment with different values of resistors, capacitors, and input signals in your simulator to further explore the behavior of the op-amp differentiator. As you become more comfortable with the concepts, you can move on to building physical circuits and observe their behavior in real time. I hope this extended discussion has provided you with a more comprehensive understanding of the op-amp differentiator and its applications. If you have any questions or ideas for future videos, please don't hesitate to share them in the comments section. Thank you for joining me in this exploration, and I look forward to seeing you in the next video as we continue to unravel the fascinating world of electronics and circuit design.